Hello, this is Pre-Calculus, lesson 1.2, day 2 of functions and their properties. Yesterday or on the previous video, I talked about a number of things involving analyzing a graph. We talked about domain and range. Just keep in mind, domain is basically what x values does the graph hit. The range is what y values does the graph hit. One way to think of that is you can, for the domain, start from left to right on your graph. Just kind of follow it along. If there's any x values that you have to skip over, it's not part of the domain. For range, you can think bottom to top. If I scroll through the graph from bottom to top, uh, if there's any y values that you then miss or have to skip, they would not be part of the range. We talked about what a function was. We talked about the vertical line test and how you can take a vertical line, drag it across the graph, and if that vertical line crosses the graph in more than one spot at any time, it's not a function. So both of those graphs are fine, but wait, right when we got to there, we hit the graph in more than one spot with our vertical line, which means that's not a function. We went through an example of finding domain, an example of finding range. Talked about continuity. What you'll see in your textbook is it'll ask you if there's any removable or non-removable discontinuities. Basically, what I want you to do, tell me, is it continuous or does it have removable, jump, or infinite discontinuity? That's how I would like you to answer your questions. So when it says non-removable discontinuity, it's talking about either jump or infinite. Talked about increasing, decreasing, and constant behaviors and how you describe the x values or you give the interval of x values that correspond to that graph. So if we're looking at this graph right here, I would describe the x values from negative infinity to negative 2 as decreasing, from negative 2 to 2 as constant, and from 2 to infinity as increasing, always using the x values. And that's pretty much where we ended up. So starting with the new information, now we have lower bound, upper bound, and bounded graphs or unbounded graphs. Basically, if you look at this top line up here, it talks about bounded below. A function, which we'll call f, is bounded below if there is some number b that is less than or equal to every number in the range of f. Any such number b is called a lower bound of f. So basically what that's saying is, if there's a lowest point on the graph, then we would name that y value as a lower bound. We would say that the graph is bounded below. A typical graph that you could refer to or think of is your basic parabola. If you have a parabola, let's say that spot is 1, x squared plus 1. Well, there are no y values that we hit below the y value of 1. That means we would say that this graph is bounded below, and its lower bound is the y value of positive 1. So that's what we're referring to when we're talking about boundedness. Likewise, it's bounded above if there is some maximum y value that we hit. It doesn't go above a certain y value. Whatever that y value is that we reach is called the upper bound. Now, if there is a maximum and a minimum that the graph hits, maximum y value and a minimum y value that the y hits, we call that function bounded. That means it's both bounded above and bounded below. The way you can, what kind of corresponds with that or goes right hand in hand with that are local and absolute extrema. You might have heard of these as local and absolute maximums and minimums. So basically, if you have a local maximum, that means that the graph kind of rounds off and has a hill to it at some point or at multiple points. The local maximum is when you have some sort of, you go from increasing to decreasing in your graph, but it's not the highest or lowest point. Um, so, I'm sorry, for maximum it wouldn't be the highest point. If you go from increasing to decreasing and there are no other points above that, and it's an absolute maximum. And basically what I would do is, what I would expect from you is, if you're finding a maximum or a minimum, what I would want is give me the actual coordinate point. So give me the xy coordinate value. The local maximum is at 410 or something like that. And likewise with local minimum. That's when your graph goes from decreasing to increasing. It's a local minimum if it goes from decreasing to increasing, but at that point where it switches, it's not the lowest point on the graph. Just be aware, if it is the lowest or highest points, those are called the absolute maximum and minimums. If it's if they're not the highest and lowest points, they're all called the relative extrema or the local extrema. So we'll do an example here. So with this example, decide whether f of x equals x to the fourth minus 7x squared plus 6x has any local maxima or minima. If so, find each local maximum value or minimum value and the value at which it will occur, or each occurs. So for this one, right now, you just want to graph it. So you take out your graphing utility, graph it. I've already done that. I've already got it in my graph. I've already adjusted my window, so you can play around with getting your window to look nice. But what you should realize or notice is the graph is decreasing, 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 and then all of a sudden it's increasing. So right here, that lowest point right there, that's going to be a minimum. And then it goes up, it goes up, it goes up, and then it comes back down. Well, right before it came back down, that would be a maximum, because it goes from increasing to decreasing. And then right away again, it goes from decreasing to increasing. So there's another minimum right there. So this graph actually has two minimums and one maximum. This lowest one would be an absolute minimum, because it's the lowest point on the graph. There's nothing below it. These two would be local. These would be local extrema. One of them a minimum, one of them a maximum. How can you find those values on your graph? It's as easy as anything else you've done. Second, calculate, and you have minimum and maximum functions. So I press number 3. That was minimum, I think. Left bound, I can pick something. Okay. Left bound, so I know I think that's -5 is to the left of the minimum. And then at -0.5 looks like it's to the right, but not past the next one. And then you get to guess. I'll guess -2. Oh, close. It was real close. -2.856, so on, is the x value, and then -24.85 is the y value. And I would want that whole coordinate point. You would say absolute minimum or absolute extrema, -2.85, comma, -24.86. Or I suppose you'd say -2.86, comma, -24.86. And then you do the same thing for the maximum and the other minimum. So that's good stuff. Uh, Here we show that. Here's just to see an answer. If you want to pause it, you can take a look. But remember, what I would like from you, don't worry about this notation that they use. Um, you don't have to do that. What I want is just give me the actual coordinate point. The next thing I'm going to mention is symmetry. There's three types of symmetry you're going to look for. Symmetry with respect to the y-axis, symmetry with respect to the origin, and symmetry with respect to the x-axis. So the things to remember about symmetry with respect to the y-axis. We call these functions even functions. If there's symmetry with respect to the y-axis, they're even functions. Algebraically, to see if there's going to be symmetry, this is what you do. This is the key. Whatever your function is, this is saying you take every x that is in your function and replace it with a negative x. If when you do that and then you simplify it, you get what you started with, the original function f of x, then there is symmetry with respect to the y value, or the y-axis. Your basic function, a parabola, very easy to see. You've got symmetry with respect to the y-axis. What does that mean? It means if you take what's on one side of the y-axis, if you take what's on one side and reflect it across or in the y-axis, you get the same thing on the other side. If you folded your paper on the y-axis, your graph would line up right on top of itself. So big keys here, algebraically to check if there is symmetry with respect to the y-axis, or to show that it is an even function, you need to be able to understand this concept. If you plug in a negative x for every x value in the function and then simplify, if you get the original function back, the one that you started with before you plugged in a negative x, then it is an even function. Symmetry with respect to the x-axis, it's the same type of thing, only it's reflecting in the x-axis. So if you fold on the x-axis and your graph lines up on top of itself, then it's got symmetry with respect to the x-axis. These would not be actual functions, because obviously that will not pass the vertical line test. Algebraically, it says graphs with this kind of symmetry are not functions. That's what I just said, except the zero function. But we can say that x comma negative y is on the graph whenever xy is on the graph. What does that mean? If you know any point on the graph, well then that same point with the opposite y value will also be on the graph. So be aware of that. And then the other real big one, just like the even function, is an odd function. If there's symmetry with respect to the origin, we call that an odd function. On this one, algebraically, and this is another big key here, algebraically, if you plug in that negative x for every x value in your function, after you simplify it down, if you get the exact opposite of the original function, then it is an odd function and there's going to be symmetry with respect to the origin. Okay, so if you basically took your graph now, graphically, whatever you have here, if you reflect it in the origin, your graph will line up on top of itself. So basically, every x, y value you have should be reflected to its opposite value, or the negative x, negative y value. Algebraically, what we're talking about, if this is f of x right here, then I'll use a different color. Then f of negative x would be negative x cubed. Well, that's the same anytime that you take an odd power. Uh, Anytime you take a negative number to an odd power, you know the result is negative. And that is the opposite of what we started with. back here. So that's algebraically showing that it would be an odd function. Okay, another big concept here that you're going to have to put a lot of time into to fully understand is talking about and writing horizontal and vertical asymptotes and using what we call limit notation. So let me back up. I'll just read this. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if f of x approaches a limit of b as x approaches positive infinity or negative infinity. So what that's saying is, if you take a look at your graph, and as you go as far as you can to the right, and or as far as you can to the left, and the graph approaches some number value, but never crosses it, or never quite reaches it, then there's a horizontal asymptote there. So it doesn't matter what happens in the middle of the graph, so you might want to make note of that. Don't think that in the middle of the graph, your graph can't actually cross the horizontal asymptote. It's what the graph approaches as you head towards an x value of positive infinity or negative infinity. So what you could think of is, you can think of if you had a function that looked like this. Okay, and let's just say, I'm not even going to draw the other part of the function. Let's just say that it never quite reached this imaginary horizontal line, because that's what an asymptote is. It's an imaginary line that your graph does not ever quite reach. So let's say this function, as you head towards positive infinity, you just never quite reach that y value of 1. Well, then there's a horizontal asymptote there. It doesn't matter, or it wouldn't matter if over on the left, over here, if there's another part of the graph, it wouldn't matter if it crossed that line. All I care about is looking at, in one direction or the other, does it approach some imaginary line and never cross it? So I mentioned limit notation before. Here's how we write that. The limit of whatever this function was, we'll just call it f of x, as x approaches infinity is how you read that. And that's how you write it. The x approaches infinity, that x arrow infinity needs to be small and huddled underneath the lim for limit. F of x is a normal size, just like limit. And then you talk about what happens as you go as far as you can imagine to the right with your x values. As you're going as far as you can to the right, does your graph approach a certain y value? If so, what is it? In this case, it'd be 1. So the limit notation for this horizontal asymptote, the horizontal asymptote is y equals 1. The limit notation to describe it is right here. So I know this is a confusing concept, but this is the idea that you need to start grasping. So when we write in limit notation, it looks like this. As x approaches negative infinity and as x approaches infinity is real small, huddled under the regular size, the limit of f of x as x approaches infinity equals some number b. Okay, so you check both ways. You check both ways. This is the same type of thing when I ask you later on about end behavior. You're doing this exact same thing, just like when you're checking for or describing horizontal asymptotes. There's also vertical asymptotes, sometimes. Vertical asymptotes are vertical, so it's going to be some line x equals a. This is where, instead of approaching negative infinity or positive infinity, you approach some x value from the left and from the right. So to show that, what we do is we're going to take the limit as x approaches some x value, we'll call it a, from the left. We'll put a little negative sign above the a to show from the left of whatever that function is we're looking at. And if it equals either positive or negative infinity, then there's a vertical asymptote there. And we do the same thing from the right. The limit as x approaches some value of a from the right, that's an addition sign of f of x. If that equals plus or minus infinity, there's a vertical asymptote there. So there's a lot going on with this. I'll have more examples, but the key is to start getting that limit notation written and written correctly. So we'll do one example, and I'm just going to throw this on my graphic. So let's talk vertical asymptotes first. Where do vertical asymptotes occur? Well, they occur where you have x values that you can't use. So if we look at this graph or this function right here, what can't I use, or where am I limited in my domain? Well, whenever the bottom would equal 0. So how do I factor x squared minus x minus 2? Well, I'd do an x minus 2 and an x plus 1. What does that mean? The x values of 2 and the x value of negative 1 are the x values that I know I can't use. That's where I would see some vertical asymptotes. So now I'm just going to show you the graph to save time here on the video. I put the graph in here, and sure enough, as you come from the left, I approach this x value of negative 1, and you could zoom in there or trace to see what the x value is when this happens, or look at your table, but you can see it goes down, and it looks like it keeps going down. Then all of a sudden, it starts back up here. And then we have it again here at an x value of 2. So what's happening there is you have vertical asymptotes. So what you would do is you would take and you would say, well, oops, let's see, it did the, sorry about that, back up. Horizontal, horizontal. I guess they didn't show the limit notation, or I didn't show the limit notation earlier. So what you would do is the limit as x, it's a little bigger for you. The limit as x approaches negative 1 from the left of this function y, they call it y right here, so I'm using y. You can write out the whole thing, equals, and now if you look back on your graph, and you won't always have to look back on your graph, you'll know soon enough how to understand where it'll go. But as you look on your graph, as we approach that x value of negative 1 from the left, where does the graph go? It goes down. So as I approach this x value of negative 1 from the left, that's what the negative sign means, it goes down towards negative infinity. So that's what I would write, negative infinity. If you approach the same thing from the right, that's what this addition sign means. What happens? Well, here, I'll show you what that means. I'm just looking at this x value of negative 1. So as I approach that from the right, so it doesn't matter what happens here, because this isn't the x value of negative 1. I've got to follow it. Okay, now I'm getting close to x value of negative 1. What's happening as I get closer and closer? It's going towards positive infinity. And so this is how I'd write the limit notation to describe that. So I only needed one of those to have a vertical asymptote, but I'm just showing you, hey, there's both. What does that mean? I have a vertical asymptote at x equals negative 1. And you do the same type of thing for the other vertical asymptote. As far as the horizontal asymptotes go, you can see the limit notation here. I'll just let you pause it and look at that. it's approaching 0. If you look at the graph, what these are saying is the limit as x approaches negative infinity, so as I head to the left, it's approaching a y value of 0. And you can look at your table, go to a really big negative number, and you can see it never is going to actually hit 0. Same thing as you go to the right. Limit as x approaches infinity of y in this case um, is going to equal 0. Because as you go to the right, what y value do you face? Hey, look at that. I didn't know I could do that. That's pretty awesome. What y value do you face? Or do you head towards a y value of 0? So that's the lesson. I think I just have some review algebra things down here if you're interested. So you can pause. Sorry the video's a little longer, but hey, that's what it takes sometimes. Enjoy!